So tonight, we're very happy to have Richard Bell as our speaker. See Richard on the screen there. Richard has been a diehard astronomer for over 43 years. He says he's had just about every astronomy-related job one can have in Kalamazoo. Kalamazoo, Michigan is big, and it has some nice museums. I've been to the Air Zoo there, and that was really quite impressive. He's worked at the planetarium, local planetarium, for 9 years, sold telescopes at a local hobby shop for 6 years, has taught introductory astronomy courses at many local colleges and universities. He's an avid observer and has completed several Astronomical League observing programs. You might comment on the most interesting ones that you've done, and if you've done any other programs recently. I too have managed to complete a few of them, and I found them an interesting way to focus your observing, especially if you're kind of new at it and you're looking for a way to get into it, into astronomy. The programs will help you do that and really build up your skills quite quickly. In the bio, I found it said that you consider yourself a budding astrophotographer, but that was a while back. So you might tell us how that's coming, and you might tell us if your astrophotography has bloomed yet. By the way, I've looked at many of your videos on the Kalamazoo site. I recommend them. They're actually quite good, all of them. And so we do recommend them for someone getting started or someone looking for information on astrophotography, or just on some of the observing pieces that you have on there. They're very good. So are you currently the president or a past president of Kalamazoo?
I am the current president of the Kalamazoo Astronomical Society, serving my 20th term, not consecutive, thank God.
Wow. Wow, the longest serving president we've had in recent history has only been 4. I'm not sure about those prior. 20 years though is, wow, you are made of stout stuff, sir. That is amazing. And as I said, Richard Bell is here to tell us all about the King of Spring. So take it away, Richard.
All right, thank you very much. And I want to thank you for the invite. Of course, one of my goals and one of the goals of the Kalamazoo Astronomical Society is to reach out to other clubs. And so I was very happy to get the invite and have the opportunity to speak to you today. If you don't know anything about the Kalamazoo Astronomical Society, I won't spend too much time talking about it, but we were founded in 1936. We are the oldest club in Michigan by far. Next year, we celebrate our 90th anniversary, and we are also, I'm pretty sure, still the largest club in Michigan. Last year, we nearly had 500 individual members with 378 memberships. We've tumbled down a bit from our pandemic surge. Now we're down, we just picked up our 315th membership today. So it's remarkable how big we are considering just how miserable the weather is in West Michigan.
And it has been.
Let me go ahead. I'm not going to keep the video on while I do this. I'm going to just share my screen because nobody cares about me. It's the pretty pictures everyone's come to see. All right. So there we go. You should be able to see me there now, or at least my screen. So this program is basically for everybody. There's a lot of beginner stuff in here, so a lot of you will probably think, I know all this, I don't need to know this, but I'll try to throw a little bit of hard science at some of you as well. So here we go. All right. Spring ushers in a new season of stargazing for many sky watchers. Among the spring stars, we find ancient heroes and mighty beasts that rule over the night. Looking closer with binoculars or a telescope reveals magnificent star clusters and distant galaxies. So now is the perfect time to tour the spring sky highlights. Don't get me wrong, though. A clear winter night can bring the best conditions out of any season. Plus, winter nights seem to have an extra sparkle. Out of the 25 brightest stars in the night sky, 18 are visible from our latitude. At least they are in Kalamazoo. Should be the same for Fort Wayne. And 9 shine brightly during a winter night. But of course, at least for Michigan, most winter nights are really like this kind of gray and dead and very cold, and of course, very cloudy. But things are slowly improving. We, of course, reached the winter solstice right around here on December 21st, usually. And ever since that day, the sun has been continuing its annual path along the ecliptic, its apparent path anyway. And it's been getting higher and higher. Things been gradually getting warmer and warmer. And coming up here pretty soon on March 20th this year, usually March 21st, most years, the sun will reach the point to where the celestial equator, the projection of Earth's equator into the sky, and the ecliptic cross. And so we will have the vernal equinox. Spring will be here, which means we get more color. No more gray winter days and nights. We get blooming trees with leaves again, and of course, many colorful flowers. And of course, we get more clear skies. And things do warm up a bit. So finally, those long, cold, and all too rarely clear winter nights are behind us, and temperatures are becoming more tolerable. By the time we get into May, that's really good observing weather. I mean, I like kind of the 40-degree range because, as I always say, it's too warm for frost and too cold for bugs. So you get the best of both worlds there. So things are getting warmer. And also, skies are getting clear. Now, this weather data is for Michigan, of course. I definitely didn't have time to gather all this data for your area, but being so close, it should be relatively the same. And so, as you can see, clear skies are gradually becoming more common, and the nights are still long enough to explore the splendors of the spring sky. I'm always surprised that April, at least historically, tends to beat out May, but I tend to find personally May tends to have more clear nights than April, but the weather data says something else. All right, so let's prepare for a spring night. If you're absolutely new to amateur astronomy, this is the section for you. So no novice stargazer should ever venture under the stars without a monthly all-sky star map. The version you see here is the one that I created for the Kalamazoo Astronomical Society, and you can download star maps like this from our website every month. So if you get on our website right now, you can download the March night sky star map that I made. So there's no better way to learn the bright stars and major constellations of each season than just doing it with a good old-fashioned monthly night sky star chart. But if you don't want to print out a chart every month and you want one you can adjust for the exact time you're out, you want a planisphere, a much more versatile all-sky star map. So basically with this, you can adjust them to the exact day and time that you venture out under the stars. And I know what you're thinking. Well, I got this phone, I got this app. Just please forget those smartphone apps. The bright screens ruin your night vision, and there are just some old school methods that will never be surpassed by technology. I know the phones are great, people love them, but there are times you got to stop looking up at your damn phone and look up at the night sky. Pardon my French. So once you upgrade to some form of optical aid, a star atlas is an absolute must. Sure, most of us use go-to telescopes these days, but a star atlas can give you some idea of, what to look at. And they are critical if you want to develop observing skills and actually learn to locate deep sky objects on your own. So I highly recommend Sky and Telescope's Jumbo Pocket Sky Atlas. I'll use several of them throughout the program here. And it has 80 star charts plus 10 close-up charts. I'll show you one of the close-up charts as well later. And the Jumbo Pocket Sky Atlas is easy to read in the field, yet it is small enough to fit in an ordinary backpack. Of course, you can print your own custom charts with programs like Starry Night, but after a while, it gets a little boring to print out your own charts unless you get them laminated so they survive dewy nights. It's still just best to get a good old-fashioned star atlas and call it good. And of course, you can download free versions of software like this, like Stellarium is an excellent program. So if you don't have Stellarium on your computer, I highly recommend that as well. It is, again, absolutely free. So with a map or atlas in hand, you'll need to come equipped with a red lighted flashlight. So indeed, using a white lit flashlight will get you reprimanded at a public observing event, or worse, at a major star party. I mean, there are people that have never been heard from again at the Texas Star Party that use white light. They just sort of vanished off into the desert, you know? So, of course, our eyes become dark adapted in two distinct ways. Everyone knows the first one. Our pupils become dilated as the sky grows darker. But the other form of dark adaptation involves a natural chemical called rhodopsin. So over a period of 20 to 40 minutes, this chemical, rhodopsin, builds up in our eyes, making them more sensitive to light. And bright lights can bleach the rhodopsin, and so you have to start the process all over again. So our eyes are least sensitive to dim red light, so that is why it is so crucial to make or purchase your own red lighted flashlight. Amateur astronomers at all levels should always bring along a pair of binoculars. Binoculars fill the gap between the naked eye and telescopes in terms of field of view, power, and convenience. So for handheld astronomical use, 7 by 50 or 10 by 50 binoculars are generally accepted to be the best since they are light enough to hold steady. In general terms, those under the age of 30 would benefit more with 7 by 50 binoculars due to their larger exit pupils. As you age, your eyes don't dilate as wide, so that's why 10 by 50s are good for old farts like me. So most of the targets that I'll discuss here require the use of a telescope. And of course, which telescope is best for you is a topic too broad to cover here. So for most of the deep sky objects discussed in this presentation, the larger the aperture, the better, of course. So in terms of price, portability, and performance, most agree that the ideal telescope to start with is of the Dobsonian design in either the 6 to 8-inch aperture range. Their aperture is large enough to bring in thousands of deep sky objects within reach. And so every object I talk about here will look very nicely through either a 6 or 8-inch Dobsonian telescope. And there's obviously a broad array of telescope accessories to consider as well. Now, any non-go-to telescope should be equipped with a Telrad finder, or if you can't use a Telrad, you can use a Rigel quick finder. The one pictured here, of course, is a Telrad finder. Rigel quick finders are more like a tower than this long, skinny thing that sits on your telescope like a Telrad. So these are one power, no magnification finders with a heads-up display, appearing to project a red bullseye onto the night sky. This makes locating deep sky objects considerably easier. Laminated spiral-bound charts are available from websites like skyspot.com. And that shows you how to align the Telrad circle against the naked eye stars to find deep sky objects. So I recommend that you have at least 3 eyepieces in your collection to cover a range of fields of view and magnifications. Eyepiece focal lengths to consider are 40 millimeter, 25 millimeter, and 10 millimeter. Of course, most telescopes already come with 25 and 10 millimeter, but a 40 millimeter gives you a little wider field of view. You could also add a 2x Barrow lens to your collection to double the magnification of any eyepiece that you already use or own. So deep sky filters can also help to better see the targets discussed here. At minimum, I recommend a general broadband filter, like a generic light pollution filter, to help reduce, again, the effects of light pollution and natural sky glow. This will make relatively faint targets, such as galaxies, and we're going to talk about a lot of those tonight, easier to see. Now, a table is another accessory to consider. After all, you'll need a spot to keep your star chart, eyepieces, and other accessories on. Camping tables are the most convenient as they're easy to roll up or fold, taking up minimal space in your vehicle. And of course, the more comfortable you are at the eyepiece, the more you'll see. As a result, bringing along a stool or observing chair is also a very beneficial idea. There are a variety of observing chairs you can purchase or even build. There are plenty of plans online. Finally, bring a notebook or a digital recorder and keep an observing log. This is something I wish I would have done when I just started out at like 6, 7 years old. So you can just refer to your observing log for many years to come. There is software such as Deep Sky Planner that allows you to store all of your observations, including scanned sketches. I know sketches is kind of a lost art today, but still, it's a great way to train your eye to sketch stuff. So, of course, I wish I could go into more detail in this, but please be sure to check out my 5-part Introduction to Amateur Astronomy series on the Kalamazoo Astronomical Society's YouTube channel. It goes into much greater detail about all the night's necessities that I briefly covered here. So let's begin our grand tour of the spring sky. So the spring night sky, much like the autumn sky, is filled with galaxies. On the other hand, summer and winter are known for targets within the Milky Way, such as nebulae and open clusters. Why the difference? The reason has to do with our orientation within the galaxy. You might think the plane of Earth's orbit, known as the ecliptic that I mentioned earlier, is parallel to the galactic equator. It's actually inclined by 60.2 degrees. So the solar system is more or less orbits the Milky Way on its side. And this affects our view of the sky during the course of a year. During the summer, the nighttime side of Earth points toward the galactic center. So that's why oftentimes summer is filled with the really bright targets along the center of the Milky Way, because that's the direction we point in at night. During the winter, we point toward the outskirts of the Milky Way. And that's toward the direction of like Orion. In the autumn, we are directed below the plane of the galaxy and look toward deep space to targets like the Andromeda galaxy. And the same is true during the spring, except we look above the galactic plane. So we begin our tour of the spring sky at Ursa Major, the Greater Bear. From my latitude, it's considered a circumpolar constellation, meaning it never rises or sets. It always remains above the horizon. Although even from my latitude, anything above the line here, like, up here, the paws and stuff, that does set below the horizon. But because a very famous part of Ursa Major stays above the horizon year round for us, it's considered circumpolar. So yeah, technically speaking, Ursa Major is not a spring constellation, but it is at its highest during spring evenings. Now, the spring sky is easy to learn thanks to the familiar stars of the Big Dipper, which is an asterism of 7 stars in Ursa Major. The Big Dipper's most useful function is to help us locate Polaris, the North Star. The stars Dubhe and Merak are what we call the pointer stars, and they're located at the far end of the Big Dipper's bowl. This is Merak, and this is Dubhe here. And again, they form what we call the pointer stars. So follow the pointer stars from the top of the Big Dipper's bowl and follow a line as far as the dipper is long, and this leads to a star with the same brightness as the pointer stars, and sure enough, it's Polaris. So Polaris is located at the end of the Little Dipper's handle. There we go, 3 stars in the handle, just like there's 3 stars in the Big Dipper. Light pollution can make it difficult to see the other two stars in the handle, as well as the first two stars in the bowl, like these two here. These are all roughly about fifth magnitude or so, but the other two stars in the bowl are easy to see. And like the Big Dipper, the Little Dipper is an asterism, sort of an unofficial group of stars, but it shares all the same stars with Ursa Minor, the lesser bear. So take a close look at those bears. Something seems out of place. They both have long, bushy tails, as opposed to the short, stubby tails bears should have. The reason for their odd appearance has to do with a story in Greek mythology. Now, Zeus, the king of the gods, descended from Mount Olympus to walk amongst us mere mortals. And one day he encountered a beautiful woman named Callisto, and they instantly fell in love. They soon married and had a son named Arcas. During this joyful time, Zeus may or may not have forgotten that he was already married to the goddess Hera. Hera became furious at Zeus's infidelity, but she was probably not surprised because this was a common occurrence in Greek mythology. Hera couldn't punish the mighty Zeus directly, so she decided to take her vengeance out on Callisto by turning her into a bear. And she was a very ordinary looking bear, no long tail just yet. Years later, Arcas, now a young man, was hunting in the woods. He came across a large female bear and took aim with his bow and arrow. So you guessed it, the bear was Callisto herself, which he did not recognize, and Callisto couldn't say anything because she was a bear. So fortunately, Zeus was watching over Arcas and decided to turn him into a bear as well. Zeus still feared for their safety, so he decided to place them out of reach in the sky, but how? He was unable to grasp them by their snout, fearing a potential bite. He was unable to grasp them by their claws, fearing possible injury because they were quite sharp. So Zeus determined the safest place to grab a bear was by their short, stubby tails. He spun them around and threw them into the night sky, where they remain to this day. And because of the bear's weight and Zeus's tremendous force, he stretched out their tails and placed them into the heavens, where we see them every spring evening. Or if you just want the short version, I know it's too late for that, space bears have tails. That's it. Too late, though. So our first deep sky targets are the galaxies M81 and M82, located in an obscure part of Ursa Major. They can be both located 8 degrees west of Lambda Draconis, which is over here. So 8 degrees west of Lambda Draconis, or 10 degrees northwest of Dubhe, the top pointer star in the bowl. Or you can also go 6.5 degrees north-northeast of 23 Ursa Majoris over here. Take your pick. Johann Bode, best known for the tidiest Bode law. You know, it's this obscure thing that can help you predict the spacing between the planets. It's a very old idea. He discovered both on December 31st, 1774. M81 and M82 are located at nearly the same distance from the sun at 11.8 and 11.4 million light years, respectively. Their apparent separation of only 37 arc minutes from Earth allows them to fit within the field of view of most amateur telescopes equipped with a low-power eyepiece. That's how often I enjoy viewing them. M81, also known as Bode's galaxy, since Johann Bode discovered it, is a type SB spiral galaxy, which means its arms are kind of intermediately wound. They're not too tight and they're not too loose. It is also a grand design galaxy with very symmetrical spiral arms. Only about 10% of all galaxies are grand design galaxies. The majority contain branches and spurs in their arms, like the Milky Way. M81 is 92,000 light years in diameter and contains at least 250 billion stars, making it comparable to the Milky Way. M81 is the largest galaxy in the M81 group, which contains 34 known galaxies. It is the closest known galaxy cluster to our own local group of galaxies. We classify both the M81 group and the local group as poor galaxy clusters, each containing tens or hundreds of galaxies. We'll meet a rich galaxy cluster here shortly. Because of its elongated appearance, M82 is widely known as the cigar galaxy. It is 40,000 light years in diameter and 10 times less massive than nearby M81. M82 is known to be a starburst galaxy, the closest of its type to the Milky Way, in fact. As the name suggests, starburst galaxies form stars at a tremendous rate. Astronomers believe that collisions or interactions with other galaxies most likely cause starburst galaxies. In this case, we believe it was a interaction known as galaxy harassment. So yeah, galaxies harass galaxies. So an interaction with M81 as recently as 10 million years ago almost certainly caused M82's phenomenal stellar birth rate. M82's peculiar appearance once led to its classification as an irregular galaxy. But infrared images taken of M82 in 2005, I believe from the Spitzer Space Telescope, revealed two symmetrical spiral arms. We just view the galaxy edge on from Earth. M51, the Whirlpool Galaxy, is located in the small constellation of Canes Venetici, the hunting dogs. However, it is best to start from Alkaid, the end of the Big Dipper's handle, and move 3.5 degrees to the southwest to locate M51. The French comet hunter Charles Messier discovered M51 on October 13, 1773. To him, it was something meant to be avoided since it could be mistaken for a new comet, because that was the whole point of the Messier catalog. It wasn't meant to be this great list of deep sky objects. It was meant to be a list of possible comet masqueraders. But now, of course, it's some of the best deep sky objects in the sky. M51 is a galaxy viewed face-on and has a diameter of 60,000 light years. You always think it's bigger than Milky Way, but nope. We measure it as only 60,000 light years. It is classified as a Type 2 Seyfert galaxy. These types of galaxies contain active galactic nuclei, or AGNs. The supermassive black holes located within the galactic center are actively feeding on material. And so, of course, this is the case with M51. Its galaxy is eating lots of gas and dust. The Type 2 designation for the Seyfert galaxy signifies an edge-on view of the dusty torus around the black hole's accretion disk. Seyfert galaxies make up only about 2% of all spiral galaxies. They were named after Carl Seyfert, who studied them in the early 1940s. The dwarf galaxy NGC 5195 is located just beyond M51, and the two appeared to be in the process of merging. However, we currently believe that no direct interaction is occurring. Deep sky images of the region clearly show that they have interacted in the past, as evidenced by this cloud of stars that surrounds NGC 5195. So there's definitely something going on between these two galaxies, but right now it looks like a pretty peaceful place, at least in M51. So the Whirlpool was the first galaxy to be classified as a spiral, thanks to the work of the 3rd Earl of Ross, William Parsons. There he is. Lord Rosse lived at Birr Castle in Parsonstown, now Birr, Ireland, in the mid to late 19th century. He built the mammoth 72-inch Newtonian reflector known as the Leviathan of Parsonstown and used it to examine those mysterious, faint, fuzzy patches of sky, the nebulae. At one time, people believed that with sufficient aperture and magnification, one could resolve all nebulae into stars. Of course, we know today that some nebulae really are clouds of dust and gas. So the enormous light grasp of Lord Rosse's telescope revealed the nebulae like never before, and he was particularly fascinated by those with a spiral shape. Astronomers began to wonder if we also live in a spiral nebulae as they discovered more of these types of objects. It wasn't until the 1920s that Edwin Hubble confirmed the existence of other galaxies in the universe. So the 72-inch Leviathan of Parsonstown had what we called a speculum metal mirror. Speculum is an alloy that's 2/3 copper and 1/3 tin. It had roughly half the reflectivity of modern day illuminized mirrors, telescope mirrors. And speculum tarnished very easily, so they often had to take the mirror out to polish it, which is what they're doing in the image here. So you can get a really good look at the speculum metal mirror here as they get it all shined up. And I just really love this photo. I've been looking at this thing for years with, classes and talks that I give like this. And after all these years, I still can't decide, is that like some thing he's wearing around his neck? Or is that just some kind of weird neck beard? I still haven't decided. So I really know what M51 would have looked like through Lord Rosse's telescope, because again, it had half the reflectivity of a modern day telescope. So here's a 36-inch Dobsonian called the Yard Scope. I don't know who owns this anymore, but it was owned by a guy named Crazy Bob Summerfield. And so I got to look through this at the 2001 Texas Star Party at M51, and it looked just like Lord Ross's sketch that I showed you just a few minutes ago. This image, of course, was taken at the 2005 Winter Star Party, and that year I got to view the Horsehead Nebula through that telescope. So it was a really cool telescope. So returning to the Big Dipper, we noticed the bent or arcing handle. If we follow the arc, we arrive at Arcturus, the bright orange-red star in the constellation Boötes, the herdsman. So it is difficult to see a herdsman amongst the stars of Boötes, because oftentimes the classical figures here don't really match up with their kind of traditional line drawings, although there's no universal way to draw the constellations with the lines, but the figures and the lines never really seem to agree with one another. So during the spring, many like to envision a diamond-shaped kite as opposed to the figure of the herdsman. So Arcturus is where the tail begins and works its way through the sky. So that's the springtime interpretation of Boötes. But during the summer, I like to envision Boötes as an ice cream cone. Arcturus is at the bottom of the cone with one scoop of ice cream on top. A U or C-shaped group of stars appears nearby, resembling another scoop of ice cream that has fallen off. This, of course, is the constellation Corona Borealis, the Northern Crown. Our next deep sky target is again technically in Canes Venetici, but it is best to start from Arcturus and move about 12 degrees to the northwest, or 14 degrees due west from Izar over here, the first bright star located to Arcturus's upper left. It might take a little extra effort, but sooner or later, you're sure to come across the magnificent globular cluster M3. So this massive collection of approximately 500,000 stars does not really have a common proper name, but since it's in the constellation Canes Venetici, it's the brightest cluster in there, I call it the Canes Venetici cluster. So this cluster was discovered by Charles Messier on May 3rd, 1764, but wouldn't be resolved into stars until the great William Herschel observed it in 1784, 20 years later. So M3 is estimated to be 8 billion years old, which is fairly young as globular clusters go. M3 also contains 274 known variable stars, by far the highest number found in any globular cluster. So this includes 133 RR Lyra stars, which are standard candles used to measure distances, much like the more famous Cepheid variable stars. However, RR Lyra stars have a mass and size similar to that of the sun. Therefore, they're usually fainter than Cepheid variable stars. So in this animated GIF or GIF, I always forget which one, many of these stars that seem to be slowly pulsating, those are RR Lyra stars. Probably not every single one of them, but you get the idea. There's quite a few in there. The constellation Hercules contains the best globular cluster in the northern sky. Hercules is a large constellation, but can be difficult to find since none of its stars are brighter than 2.75 magnitude. A quick way to track down Hercules is to start in the middle of a line drawn between Arcturus and Vega, the brightest star in the summer constellation Lyra, but move slightly toward Vega. So, yep, just draw a line between the two, go in the middle, go to a little toward Vega, and you're sure to come across the constellation Hercules. And so you're sure to find the asterism known as the Keystone, which is also the body of Hercules himself. And like the keystone at the top of an arch. So the globular cluster M13 is located just 2.5 degrees south of the star Eta Herculeus. For a beginner, it's a really easy star hop. And this is the northwest star in the keystone. So it's very easy to find both the keystone, at least once you know how, and then from there, it's really easy to find Hercules. At magnitude 5.8, M13 is visible to the unaided eye under pristine sky conditions and easy to spot in a pair of binoculars. Most interestingly, no one would discover M13 until 1714. Edmund Halley of comet fame spotted it with the unaided eye. How the ancient sky watchers missed it, though, is a genuine mystery because, again, it's not hard to see, and they followed the night sky much more intently than we do today. M13 is about 145 light years in diameter and contains approximately 300,000 stars. So M3 may have 200,000 more stars, but M13 is 11,700 light years closer to us. M13 is 22,200 light years away, which means we see it as it appeared 22,200 years ago. That's what we call look-back time. Light from M13 dates back to the Upper Paleolithic or Late Stone Age, where we find the earliest known evidence of organized settlements. Age is one area where M13 clearly wins over M3. It is about 11.65 billion years old, fairly typical for a globular cluster. Globular clusters contain population 2 stars, which are old and metal poor. So in astronomy, The term metal means elements more complex than hydrogen and helium, even like, oxygen is considered a metal in astronomy. So the stars of M13 formed at a time when the universe was composed of nothing but hydrogen and helium and just a trace amount of some heavier elements. So globular clusters like M3 and M13 are located within the galaxy's halo, kind of this cloud of stars and globular clusters that surrounds the central bulge of the galaxy. They orbit the galaxy in highly inclined elliptical orbits. M13, for example, takes 500 million years to orbit the galactic center once. Its orbit takes it as far as 800,000 light years from the galactic center. For our next deep sky target, we move on to Leo, the lion. Now, Leo is simple enough to locate on its own, but we can return to the Big Dipper if you need help. We'll again use the pointer stars, but now we'll follow the line in the opposite direction. This takes us between stars shaped like a right-angled triangle and a backward question mark here. There we go. An asterism known as the sickle is the backward question mark. The sickle is really, of course, Leo's mane and head, while the bright star Regulus represents the lion's heart. The nebula, the brightest star in the right-angled triangle, is the lion's tail. Area is tough guy. So the origin of the celestial lion can be traced back to the Babylonians, where it was later inherited by the ancient Greeks and became an important part of their mythology. The Greeks believed the lion originated from the moon and later fell to earth to torment the people of Nemea. So the Nemean lion was much larger than his terrestrial cousins, and his coat was impervious to fire and metal weapons. The terrified people of Nemea were so desperate for help, Zeus sent his young son Hercules, the strongest man in the world, to kill the lion in the first of his 12 labors. After failing to kill the lion with spears and arrows, Hercules wrestled it to death and then skinned it with his own claw. But even though the Nemean lion was very tough, he is not the king of spring. That has yet to come. Moving 2.5 degrees southwest of Theta Leonis, on the opposite end of the nebula, in the right-angled triangle, or also known as Sheraton. The other star at the base of, again, Leo's right-angled triangle there, leads us to the Leo triplet of galaxies. The Leo triplet members are M65, M66, and NGC 3628. He's just kind of a latcher on there. He's not part of the Leo quartet, but we have the Leo trio there. So these galaxies are known as the M66 group. They may be part of a larger cluster with the M96 group over here, located just to the west. So Charles Messier discovered M65 and M66 on March 1st, 1780, while William Herschel discovered NGC 3628 on April 8th, 1784. And both M65, M66 are about 35 million light years away, while 3628 here is the one that's 36 million light years away. If the distances of M65 and M66 really are both 35 million light years, then their separation can only be about 200,000 light years. Compare that to 2.5 million light years for the Milky Way and the Andromeda Galaxy. So they are very, very close compared to those two there. M65 is what's called an intermediate galaxy. It's about 94,000 light years in diameter. So by intermediate, I mean it's currently in a state between a regular and a barred spiral galaxy. It kind of has properties of both. So this galaxy is low in gas and dust. I should say relatively low in gas and dust. So there is little star formation going on in this galaxy. About 800 million years ago, M65 may have weakly interacted with the other Leo-tropic galaxies, resulting in a slightly warped disk. M66 is also an intermediate galaxy, measuring about 87,000 light years in diameter. And in stark contrast to M65, it is rich with star formation. Its warp shape is likely a result of interactions with NGC 3628. So, NGC 3628, also known as the Hamburger or Sarah's galaxy, is visible at 3 degrees from edge on. To me, it always looks like Mr. Peanut, so I call it the Peanut Galaxy. And anyone that knows me knows I love edge-on galaxies, and this is one of my absolute favorites next to NGC 4565 and Coma Berenices. So the galaxy itself is about 78,000 light years across, but deep images of the region reveal a 300,000 light year long tidal tail of stars. This is no doubt due to its interactions with M66. The faint upside down Y constellation Cancer the Crab is just west of Leo. M44, the Beehive cluster, is located just west of a line between Acilus Borealis and Acilus Australis, you know, the northern one and the southern one. And so the Beehive is easily visible under dark sky conditions. So it may actually be the only deep sky object that is easier to find than its parent constellation. You know, you can't really say that about any other deep sky object. So that's kind of strange because the stars of Cancer are pretty faint. So indeed, at 3.7 magnitude, it has been known since ancient times, the Beehive that is. M44 is also known as the Praesepe, Latin for manger, and at 577 light years is one of the nearest open clusters to Earth. The Beehive's core diameter is about 23 light years and contains about 1,000 stars, making it a grand sight for binoculars or a wide field telescope. The cluster contains 60% M-type red dwarfs, 30% sun-like stars, F, G, and K, and 2% A-type stars. Moreover, the cluster encompasses 5 giants, you know, big stars, 11 recognized white dwarfs. In September 2012, researchers discovered 2 planets orbiting separate stars, both of which are hot Jupiters, within M44. Now let's again return to the Big Dipper and follow the arc to Arcturus, and we'll continue in a straight line to Spica, a bright white star in the constellation Virgo. So just remember, follow the arc to Arcturus and drive a spike to Spica. So if you can remember that, you can navigate your way around a lot of the spring sky. Above Spica is a V-shaped group of stars reminding us of the constellation's name. The V represents Virgo's outstretched arms, reaching up to gather the warmth of the sun. From Spica, there's a faint curve of stars marking one leg. This one only shows like a short line there, even though it's really more of an arc. And so there's another kind of parallel line showing her other leg. So this is what Virgo is supposed to look like. But again, the figure doesn't really match up with the stick figure because she's not holding her arms up in the shape of a letter V. So, oh well. whatever. So from Spica, move 11 degrees to the west or 10 degrees south of Porima. Up here in Virgo there, Gamma Virginis. And then you move, and then you'll encounter M104, the Sombrero Galaxy. Pierre Méchain, Messier's assistant, discovered this galaxy on May 11, 1781. The galaxy's nucleus is very star-like. And the dust that divides the galaxy in half is really easy to see, as you can see in this sketch here. And in terms of absolute magnitude, as opposed to apparent magnitude, which is 8, M104 is the brightest galaxy within a radius of 32.6 million light years, about 1 megaparsec around the Milky Way. M104 is about 50,000 light years in diameter, about half the size of our galaxy. However, it is surrounded by 1,200 to 2,000 globular clusters. Our galaxy is currently known to contain just 158 globular clusters. The center of M104 contains a supermassive black hole of about 1 billion solar masses, while a 4.31 million black hole exists in the heart of our galaxy, the Milky Way. It is a delightful sight in a telescope. When I look at this galaxy, the Mexican hat dance song always plays in my head. Hey, okay, there we go. Okay, so for a long time, M104 was believed to be an edge-on spiral galaxy, but the infrared Spitzer Space Telescope discovered a larger and more massive halo than previously believed, indicating that it may be a giant elliptical galaxy instead. Our final deep sky target is located halfway between the stars Venda Beatrix here, or Epsilon Virginis, which is a lot easier to say, and the nebula in Leo. It is none other than M87, the unchallenged king of spring. So yes, ladies and gentlemen, this is it. M87 is the title object of the presentation. This is the king of spring. I know what you're thinking. Hey, Richard, I've looked at this galaxy before. It's just a little fuzzball. Well, hang on there, because any amateur astronomer knows sometimes you have to use your mind's eye as well as your eyes when you view these things. So have some respect for your king, because it is the king of spring, and I'll try to convince you of that here now. So Charles Messier discovered M87, also known by its radio source name Virgo A, in 1781. And you can see it's located at a distance of 53.5 million light years away. So it is a supergiant elliptical galaxy, again located about 53.5 million light years away, with the brightest portion measuring about 120,000 light years in diameter. Its galactic envelope extends out to 490,000 light years. Its diameter may not seem too impressive when compared to the Milky Way, 100,000 light years, but M87 is spherical in shape, while our galaxy is, pretty flat. Its impressive volume includes an estimated 2.7 trillion with a T stars, and that's probably on the low end of the estimate scale. So compare that to the Milky Way's population of 400 billion stars. An abnormal number of at least 12,000 globular clusters surround M87. M87's total mass is at least 200 times that of the Milky Way, making it one of the most massive galaxies in the local universe. The center of M87 contains a supermassive black hole with a mass of at least 3.5 billion solar masses. 3.5 billion. Upper measurements place that at 7.22 billion solar masses, which would make it one of the most massive black holes in the entire universe. A relativistic jet of matter 6,000 light years long can be seen traveling out of its nucleus. It is possible to see this jet for yourself through the largest amateur instruments. This is on my astronomy bucket list. The jet extends even further in radio waves. There is evidence of a counterjet, but it remains unseen due to a phenomenon known as relativistic beaming. I'll let you research relativistic beaming on your own because that would take a while to explain. So here are the way that supermassive black holes are constructed. So the theory predicts that the central cavity in the disk where the black hole lurks may be very narrow, but that the disk there is puffed up and thick. This means that the black hole is hidden deep inside this narrow central well. The outer part of the disk, according to calculations, and we have visual evidence of this, is a fat, dense donut or torus of dusty gas. So we mentioned that earlier when we talked about M51 being a type 2 Seifert galaxy and how the dusty torus here blocks our view of this region here. So here's kind of a computer animation of what this might look like if we could visit it up close. So you can see the black hole is a pretty tiny feature in an otherwise ginormous, supergiant elliptical galaxy. And I feel sorry for any planets along the beam there, but remember, these are also composed of population 2 stars, meaning they're very metal poor, so there are probably no rocky planets to get destroyed along the beam anyway. So M87 is located at the heart of the Virgo cluster of galaxies, a rich galaxy cluster with about 2,000 members. And so here you can see M87 located right at the center of the cluster. You can't really tell it's at the center in the image here, but this view gives you a better sense of that. So there's M87 right there. So the Virgo cluster subtends a maximum arc of approximately 8 degrees centered in Virgo. And again, M87 may be the most massive galaxy in the cluster, but the elliptical galaxy M49 down there is actually the cluster's brightest. So we know the sun, maybe here, is about 2/3 from the galactic center in the Orion Cygnus spiral arm, but let's travel outward. Here we see the Milky Way and the large and small Magellanic Clouds that we believe orbit the Milky Way galaxy. So those are two of our satellite galaxies. There's the Andromeda Galaxy and M33, the Triangulum Galaxy. So we can pretty much see the local group of galaxies here, which contains about 55 members. And now we see another galaxy cluster here. So this could be the M81 group with M81, M82, and friends. That is also a poor galaxy cluster with just about 35 members. And now here's a rich galaxy cluster. This could be a mock-up of the Virgo cluster of galaxies. And as we have come to learn in recent decades, both our local group of galaxies and the Virgo cluster are part of a supercluster of galaxies. That galaxy metropolis was previously thought to be the Virgo or local supercluster of galaxies. However, astronomers at the University of Hawaii and the University of Lyon discovered in September 2014 that the Virgo supercluster is in fact merely a lobe of a far larger supercluster. Dubbed Laniakea, Hawaiian for immense heaven, it contains 300 to 500 galaxy clusters. Overall, the Laniakea supercluster of galaxies has a total population of 100,000 galaxies. The Laniakea supercluster is located in the Pisces-Cetus supercluster complex. A galaxy filament, like say one of these here, estimated to be about 1 billion light years long and 150 million light years wide. So the Virgo supercluster lobe, as I call it, which contains the Milky Way, accounts for only 0.1% of the total mass of this complex in the Pisces-Cetus supercluster complex. And as you can see here, great voids of near nothingness, no particles, no nothing, lie between these extensive filaments and walls of superclusters of galaxies. Every little bright knot is a supercluster of galaxies. So this is the large-scale structure of the universe, also known as the cosmic web. So what is your complete cosmic address? So you can put this on your envelopes here from now on if you still send envelopes. So you put your name at the top here if you want, then add your home address, where you live or where you are now, either one's fine. Add in your city, state, or province. So for me, Kalamazoo, Michigan. For you folks, Fort Wayne or Indiana. Put in your country, US of A for most of us, I believe. Your continent or island, because I have given this presentation for people around the world. So, of course, we're in North America, which is located in the Western Hemisphere of the planet Earth, which is in the solar system, which is in the Orion Cygnus spiral arm of the Milky Way galaxy, which is part of the local group of galaxies, which is part of the Virgo supercluster lobe. Again, my name for it. You probably won't find that anywhere else. And that's part of the Laniakea supercluster of galaxies, which is a member of the Pisces-Cetus supercluster complex. That's the galaxy filament that we live in, and that is located in the universe. So that is your complete galactic address. That is where you are, at least in space, but not time. So amateur astronomers can only view a small portion of the universe through their telescopes on a clear spring night, but our mind's eye can take us much further. So thank you for listening, and clear skies. There you go. I hope everyone enjoyed that.
Yes, Richard, that was incredible. Thank you very much
You're very welcome.
for that. So we have time for some questions. So let's see if anybody has any questions. I have a couple, kind of kick things off. First question I have is if you could go back to the picture of Rose's telescope where they were polishing the mirror.
Oh, sure. You want to see that again?
Yeah, I'd like to see that again.
Yeah, let me.
Interesting cast of characters in there. You point out the guy that was wearing the
neck beard?
The net white collar. I would like to think it'd be a bizarre beard, but when you have nothing better to do, maybe growing a beard is the best thing to do.
There we go.
Yes, okay. So the man on the left, standing on the first stair there, he appears to be holding a sledgehammer, and the man above him is holding a, I don't know, something like a ball peen hammer. What do you suppose they would do with those?
They may have tried to use that to reshape the mirror a bit. That's my guess. I mean, it is metal. It's not glass, so it could probably take a bit of a pounding.
Sort of like a golf ball, then. That is quite an amazing picture. That's a real picture, huh?
Oh, yeah, absolutely.
That's amazing that he could do that. So thank you. I just wanted to humorously point out the delicate sledgehammer that he was holding.
Yes.
That's second question. many of the pictures that you showed look like they may have been yours. Who did most of the photography? Not your grand finale. That was truly a grand finale, by the way. Thanks for that.
No, I'm my own worst critic. I have a pretty decent image of, like, say, M51, but I often don't. I'm not ever happy enough with my work to really show it unless it's on this, like, a web page where I'm not around to have people snicker at it or anything. So usually, hopefully, with most of the images you saw in the program, you know, I may have made them a little small, but I tried to give credit to every image that I found online that I liked from other people. So I always try to give credit where credit is due.
Yeah, I didn't see those attributions, but you're right. That is always a great thing to do. So those are those, and very impressive, and the animations were very good too. Thanks for that. Anybody else have questions? Anyone? No? Please? Ben, go find the microphone first. Thank you. It should be on. You don't need to hold it that close. If the green light's on, you're good. Yeah, just maybe I should go bail him out. Right there. Oh, there he is. No. What's the matter, Ben? Is it not on here? Use that.
All right. Hello.
Oh, it is on.
Hi.
Maybe. Go ahead.
Okay, there's green light. Okay, yep. So it was a really nice presentation overall, but more of a comment when you declared M87 the king of spring. I got very excited, but you didn't mention the Event Horizon Telescope. The
No, I figured, what did I go? A little over an hour, so I figured I better
take for time.
Take some stuff out. Yeah.
Okay.
Can't mention everything. There is a lot to mention.
Yeah. Oh, just some amazing images, and just the technical feat of getting all those telescopes to work together at once. It's just quite a feat. So
if you go to our YouTube channel, there is a 90-minute version of this talk on there. So I tried to shorten that a bit for you folks.
Okay.
I'm kind of known with a tendency to ramble on for a bit just because I love this stuff so much. It's so much fun.
Thanks again. Anybody else with questions? Oh, yes.
What's a good portal sky that you would start doing this at? Would you what darkness?
I'm sorry, I missed the question.
What's the Bortle sky that you normally shoot in, and what do you think the view in?
Yeah, the skies around here aren't terribly great. Normally, these days, when I go out to image, I go to the Kalamazoo Nature Center where we have our observatory called Owl Observatory, and you know that's just like 5-6 miles north of downtown Kalamazoo, so it's like a Bortle 5 or 6 site. So it's not the greatest spot, but during the majority of the year, like right now, these days I don't venture out much anymore. I use our remote telescope in Arizona, where it's a Bortle 2 site. It's very dark there.
I think StarQuest is around a Bortle 5. I have to look again, but it's around a 5. And on a good night, it's a bit better than that when you have less dust.
Oh, you kind of cut out there. Still don't. And I don't know if you folks can hear me, but I just want to say for the record, I am not related to Kathy Bell. Hi, Kathy. You can send me a Christmas card, though. I don't mind. You guys have totally gone silent. Well, you don't need to hear from me anymore anyway.
And now you should be able to hear us.
There we go.
Not really sure why it dropped out. You'll have to try to-
Sunspots.
Yeah. But we're to solar max, so propagation should be good. Anyway, I think that's it for the questions.
One clarification,
Yes,
that 90-minute, show that he was talking about, the, address for that again?
it's on their website,
Oh, okay.
but and we have the 5 presentations on there, so you should be able to get it from there, and
Okay.
I
Yeah.
can give you a hand with that. You can
Just go, just do a search for Kalamazoo Astronomical Society on YouTube and you'll find our channel.
Thank you.
Yep.
Very good.
There's a lot there.
All right, again, thank you very much, and we appreciate it.
You are very welcome. Thanks for inviting me again.
You're welcome to stay on board if you'd like. I think if anybody brought some
Sure.
images.
Yeah.
just
Daredevil
know.
doesn't come on until 9, so I'll wait for a bit.
Either of the eclipse or anything else, we'd be happy to take a look. Anyone? No one?
This was 2403 Phil convinced me to take a picture of this. It sort of came out okay, you know. Yeah.
M78 there.
Yeah, I missed it. And this is Uranus, and you can see these are the 2 Titania and Oberon, 2 satellites. That was kind of cool. That's just the cluster M34.
Go back one.
Yeah. Hello. Yeah.
Oh, that's good.
Uranus, if you want to be politically correct, maybe, I don't know. Yeah, and let's see. I think I got, yeah, M57 came out okay, you know. Yeah. Oh, and this was kind of cool. This is the asteroid Flora, and I didn't know how to show this really well, but I basically set it up to take a picture every hour for about 10 minutes, you know, and then I stacked them all together, so you get kind of a fuzzy spot where the asteroid was, but it, you know, it's kind of cool that you see that.
See the relative motion compared to the.
Yeah. There's
Cool.
M87, he was talking about that, you know. A couple more galaxies, you know. I think it's probably enough. Ooh, M92, everybody likes globulars, you know,
There you go.
and then 891. Yeah, okay.
That's nice.
So I'm trying to knock off all the Messiers, and I'm getting about halfway there already, so.
You have to stop.
We're there.
There you go.
Yeah, it's hard with one screen.
All right, got an improved version of Orion with this is all C-Star S50. And then one that I really didn't get last year that I wanted to get this year was the Horsehead.
Yeah.
And also got the nice nebulosity up here by Alnitak as well, so that turned out well. I was surprised I did a 20-minute exposure before, could barely tell where the Horsehead was, and this time, like by 10 minutes, I could see it. It was just a lot better conditions, but I still went 40 minutes on the exposure. This is some for you C-Star users, this is something I wanted to show you. There's a new feature on there that you might have not noticed yet. There's an AI denoise button.
Yeah.
And you see that on the menu while you're imaging. And if you click it, it'll take 15 or 20 seconds and process that image. And then you can save that. But meanwhile, the telescope's still imaging and you can go for a longer you can keep going for a longer exposure. But this is the normal C-Star image. And that's cleaned up. I'll go back and forth, so. It's,
Yeah.
it's, yeah. No, it's like AI, like artificial intelligence is what I'm assuming is. So it really takes out a lot of that fuzzy background that you get, so. I wish I'd done that on the horse head, but I don't think the night I did the horse head, it was on the menu yet. Also, the Pleiades is too big for the normal field of view with C-Star, and C-Star now you can expand the view, and then it takes multiple images and merges them together. I did this at home one night, and this is what I got. Obviously some problems. But then I went back the other day at the observatory and rotated the field so I could get the Pleiades in without quite so much extra field, and got a much better image. And then this is the AI cleaned up version of that. You still get the nebulosity in there, but you get rid of a lot of that noise.
Right.
So, but this is a really slow process. You got to be prepared to let your telescope sit there a long time to put one of these together, these mosaics together.
3 or 4 beer.
I mean, you might just take a 6-pack. And then this is 1 o'clock on Thursday last week, 1:20, 1:40, 2 o'clock,
Mhm.
2:20, and 2:25. So just going, I wanted to point out, some of you are spaceweather.com viewers like I am. They explain why the edge of the moon looks bluish here. And I think yesterday's or day before yesterday's space weather, the ozone layer at the top of the stratosphere absorbs red light. And so at this point, the light that's hitting the moon is going through the stratosphere. Some of the red is absorbed, and so it has that more of a bluish cast than normal. So I found that interesting. So I read that, and then I went and looked at my photos and going like, oh yeah, sure enough. And let's see, 2:40, and my last one, I took one at 3:10, but I don't think I have it on there. This is 3 o'clock. So the C-Star did pretty well. It's the first time I've done an eclipse with the C-Star.
Yeah, sorry, I couldn't get the video up.
But that denoising thing, I think, is really nice.
Does anybody on the Zoom call have any images they'd like to show?
I got one.
Okay, Richard.
All
Go
right, here we
ahead.
go. Here you go.
Ah,
There you go.
ooh. Which stars are those?
These two I don't know, but there's a couple up here that I identify on our Facebook page. I didn't write it down though, but what I thought might have been a wide double is really just an optical double.
Hmm.
This is taken with a 5-inch or 130 millimeter stellar view on a astrophysics Mach 1 GTO. And a Canon 6D. It's a 6-second exposure at ISO 200. Just a little tweak in Photoshop. I was quite surprised this time when I pulled the images off the camera, or really they downloaded. I barely needed to tweak them. The colors look so good, which is really unusual. Usually they're a little faded, but this time they look really good. But I did boost them here just a tad. So there you go. And I just wanted to mention, we put our meetings on Zoom as well. We do, hybrid meetings like you guys do. And I just wanted to extend an invitation to attend one of our general meetings in April. We have Dr. Nicole Zellner from Albion College, and she's just fantastic. So if you want to check out our schedule page, please join us on Zoom. It'd be great to have you.
We'll do that. Thanks. Thanks for the invitation.
You're very welcome.
Phil Hudson has some pictures. You just plug them right in. We'll see if we can figure out how to do this. Right, open slide. All right, there you go.
Got it.
You got it. You're cooking now, Phil. Go ahead.
Okay, this is the dwarf versus the Sea Star 50.
Why don't you come around and so we can see it?
So, yeah, so those are both 100% images, just comparison. So you can see, I called Jim and he sent me that NGC his, and it
came out pretty good.
came out great. So,
How many hundreds of subframes do you have here?
these were about 30 minutes, didn't we? Both
Yeah, I
go
don't know.
about the-
Yeah, I tried to run an hour, but it throws out a lot, so it's probably about. the same.
Okay, can you advance it?
How about
There.
that one?
This is the Tony Eclipse, and these are strategically placed, but it is composition, and that's the field of the sea star, or the dwarf.
Yeah. That's fine.
Okay, and then the next one is just the little eclipse
Uh-huh.
photo, and then on the egress of the eclipse, next slide,
It
please.
almost looks like Richard's.
Yeah.
Ooh, Bailey's beads.
We did, yeah, we did get a little haze up there, but I thought that was an interesting picture. And then the last picture is, that is the Cone Nebula, and that is shot last night in Border 9 skies, so,
Wow.
Portal 9.
yes,
Yeah.
It's your house.
at my house.
Back
Yeah.
up one frame,
Uh-huh.
and are we seeing that blue across that you're talking about?
Maybe a
Caused
little.
by the absorption?
Or maybe here, right here.
Oh, here?
No,
Yeah.
it's across the face of the moon.
Yeah, a little bit here.
Yeah, they
Yeah,
zoom in, yeah.
the red
Oh,
and white
I'm sorry. I didn't know I could do that.
looking blue,
Hey, you learn something every day.
I do.
which would, they were saying that's caused by
Ozone.
that's
Ozone?
the stratosphere, the Earth's stratosphere,
Yeah.
filtering out the blue, or the red. The red.
My exposures went from 1,000ths of a second, or 1,000th of a second to 4 seconds at totality. I don't know how many stops that is. It's about 14 stops. Amazing,
Wow.
you know.
That's a
So,
lot.
yeah, maybe back up to the composition. That would be kind of fun to see.
That is pretty cool.
Yeah.
Like that. What's the star field that they're on?
It's a star field that totality was in, and that's for the planetarium program.
Uh-huh.
But I have the center star, that's this star right here, and I'll go back and shoot that and then put that in, you know, eventually.
You have a lot of great, you have a lot of imagination.
It's like you used to do this for a living. Is that it, Phil?
Yeah, let's go.
Oh, okay.
That was cool.
There, how do you like that? Is that cool? That is really, really cool. So what we're looking at here is Betelgeuse. It's an M, depending on what part of the variable cycle it's in, it's either an M1 or 2 red giant. And we're looking at a fairly restricted range on this. The spectroscope is set up for monitoring the blaze star when it pops. And the point of that exercise is to get as many helium lines as I can. And you'll notice that there are no helium lines in emission and not even really in absorption along the face of what we're looking at here. The key characteristic of an M star are these titanium oxide lines that you see, and they're all over the place. Some are very steep, some are very, very pronounced, like this one at 4955. So M stars are so cold that molecules can exist. Titanium oxide is one of them. There are only a handful of others. This magnesium magnesium, I don't know, hydroxide, something, it's not a hydroxide. Anyway, that's a molecule as well, and it's in absorption right there, so we have a nice peak. So this is what a standard M star looks like. So when you go to the blaze star, it's also an M type. It's a binary pair of an M type and then a white dwarf. And then between them, you've got this accretion disk that's formed between them because of the orbits and the size of the red giant. You end up seeing the accretion disk starting to go into emission when you get enough energy coming off of the white dwarf in the form of ultraviolet energy. As it heats up, you start to see these emission lines. So this is hydrogen beta right here, this peak, and you see again the titanium oxide lines nicely line up with a standard M-type star, and so when it gets closer to going, we should see these helium lines, helium 1 and 2 lines, starting to go into emission, and the hydrogen lines starting to get a lot more energetic, a lot taller. Now the ranges don't match on these, so that's why the top side star is not quite overlaying completely. If it did, we would see hydrogen gamma here, but it was a different micrometer setting, so we were looking at a slightly different range.
So you have Juice and PCB on the same plot here?
These are just overlays using plot spectra. So they're not in this, they weren't taken at the same time. They're taken at different times, different days.
So you're just comparing either.
I am. I just wanted to illustrate the point that a standard M star doesn't have any emission lines in it. It's all absorption lines, and it's dominated by these titanium oxide lines. So this one was taken a couple of weeks ago, going on a couple of weeks ago now, 3-3. And you can see some significant differences between them. One of the significant differences is hydrogen beta is wildly taller than what it had been about almost a year ago. We're getting a helium emission at 4685. So this is telling us that the accretion disk is getting more massive, and the whole system is heating up and causing the helium lines to start emitting. So once it actually goes into nova, we should see all of this stuff light up completely. But you can tell that the blaze star is in fact an H type just because of all the titanium oxide. We've got H beta growing. We've got a helium 2 line. And I think we've got 1 or 2 others in emission here, if I could find them quickly, and I can't. Oh, I've got that one, and that's titanium. That's titanium. I thought there was yet another one, but oh, right here, we've got a helium 1 line in emission. That looks like a nice overlay for that. So I'm not exactly sure how the progression is supposed to go based on the physics involved, whether or not these things go in random, the helium 1 and helium 2 lines, whether they go in random order, or if there's some sense, there probably is some sense and physics behind why they don't all appear to light up at the same time or light up in some particular order. I asked Ben about that, and we've come to no conclusion on that.
I don't think there's a consensus in the community of what really is supposed to happen.
Yeah, exactly right. And the previous novas that have gone off, that they do have good spectra, they don't really apparently have the physics quite figured out even with those. And they are quite interesting. They do have a lot of these emission lines going, but we do know that it is coming from the accretion disk, especially when it's coming in close contact with the white dwarf.
Hydrogen beta is definitely larger. Is it getting wider, or is it just?
Yes, it
getting
is.
wider?
Yes, it definitely is. Now, part of the difference, you would think that since we're seeing the red giant in both of these, where all of these stair steps are, that the continuum line should overlay better than this. The problem is that the night that I was shooting on 3-3, it started out just coal black. It was a wonderful sky, best sky I'd seen around here in many months. And by the time, and the blaze star isn't coming up until like after midnight. So by the time the blaze star was up high enough to actually take these, started to have haze, and then started to have cloud bands rolling through. So not only did the transparency go bad, the steadiness also goes off as well. So I think part of that contributed to the difference in the intensities of these red giant stair steps here. But even so, the hydrogen beta really comes through very strongly. It's obvious that it's getting hot, and we're getting closer than we were a year ago. Will it be this year? Maybe. We'll see. We'll have to keep an eye on it. So that's all I had. I just wanted to go through that. And if anybody had any other questions that I could answer, I'd be happy to take them. Otherwise, if you ask questions I don't know about, I'll refer them to Ben, or we'll just ignore it. So otherwise, that's it. And we're adjourned. So thank you very much for coming tonight. Appreciate it. Great turnout. Richard, thank you very much.
You're very
And
welcome.
please see Gene. We've got some things to sell.